Before I introduce today's speakers, I want to place today's session in context. It's called Decarbonizing Difficult Sectors in the Midwest. Yesterday, you heard our keynote speaker, Saul Griffith, explain the best and possibly only route to decarbonizing rapidly enough to avoid disastrous climate change impacts is massive generation of renewable electricity and replacement of 1 billion small machines with their fossil-free counterparts. So his thesis is the next time you replace or install a car, water heater, furnace, oven, or range, it has to be fossil-free, and that 100% adoption rate is needed. In this session, we'll hear some stories about how this race to decarbonize plays out in the trenches, rather than pencil and paper in a gifted engineer's notebook. Iowa is following this electrification approach. On the supply side, our electrical power production, Iowa's electrical carbon intensity has been decreasing at 8% per year, which is fast enough to meet the Saul Griffith view of the world. But residential, commercial, and industrial fuel use, so emissions from the use of natural gas and propane, are growing at 1% per year in Iowa. This was not helped by the 10% increase in electricity prices in real terms and 42% decrease in natural gas prices from 2007 to 2019. That had benefits to our pocketbooks for those that are using natural gas, which we appreciate. Show of hands, who has an electric oven or cooktop? About half. Okay. Show of hands, who has a heat pump water heater? 1 or 2. Show of hands, who has an electric heat pump heating their home? 2. Okay, and for those who are online and don't know how many people are in the audience, there's about 25 people here. So these single-digit responses are, a low adoption rate, if you will. Our failure to move the needle in this part of the sector is a mix of factors. Sometimes the technologies exist, but it's a public adoption, builder adoption, law, financing, and state and local policy challenge. So I hope there are smart and ambitious builders, lawyers, and policy folks listening. And sometimes we're talking about cases where the replacement technology does not exist or is just inferior or too expensive. Finally, we have, in a sense, too many alternative options in Iowa, kind of a paralysis of riches. We have corn ethanol with CO2 capture, biodiesel, methane from manure, cellulosic bioenergy, large existing hydrogen and ammonia infrastructure, and all of these options can be tied together in creative ways to solve this problem. We've lined up 4 panelists who can help us start to unpack some of these issues. I've asked them to limit 12 minutes each so that we have time for Q&A. I'll unmute and give warnings at 3 and 1 minutes. I've asked them I've seeded them with a couple questions that we'll either get to in Q&A or during their presentations. Our speakers are Benoit Geny from the Hydrogen Business Unit of Engie, joining us from Belgium. Matthew Go is stepping in for Grace Park Bradbury, if you're following your program here. They're both from Block Power, which specializes in conversion of buildings to high energy, high efficiency electric heat pump systems. Mark Embaugh Wright, Associate Professor of Mechanical Engineering at Iowa State, who has extensive experience in designing and costing bioenergy systems, will be speaking. And Ben Fish, Director of Utility Operations here at the University of Iowa. We heat and cool this campus with steam. And Ben has been a key member of a team that's been working for many years to figure out how to do that with a low carbon footprint. And he's also part of a team that's trying to design this system for the next 50 years to see how it can continue to evolve to a low carbon state. So thank you to our speakers. A little round of applause to get them going. And we'll turn it over to Benoit.
Yeah. Do you hear me well? Charles?
Yes.
Okay, great. So first of all, thanks a lot, Charles, for giving me the possibility to participate to this webinar. It's really a great pleasure for me. So can you see my slides, or do I have to project them?
We cannot see your slides. You can share your screen. They're up now. We see your desktop.
Okay, that's fine. So you can see my desktop right now, right?
Yeah, it looks good.
And now?
Looks good.
Okay. So what I wanted to present today is basically two parts. First, so since we just have 12 minutes, first part would be on really basic notion on hydrogen, so that we are sure to speak the same language. And the second part on a project that we are developing in Australia to decarbonize production of ammonia. So, and maybe prior to that, I can quickly introduce myself. So I'm Benoît Génin. I'm a business developer within ENGIE, business developer in the green hydrogen sector. I'm currently based in Brussels, but will move to the US in Houston in a couple of months. So coming back on the presentation, so in these slides, and I hope you can see it, which present different kind of production of hydrogen. And I'm going to put it in full screen. In this slide, you can see the different way we can produce some hydrogen. So maybe for some of us, some of you, it's pretty obvious, but just to make sure that we are all aligned, the first way to produce hydrogen is using natural gas or fossil fuel, basically, using a technology called SMR for steam methane reforming. This is a chemical reaction, and thanks to that, you can produce some hydrogen. Unfortunately, for each ton of hydrogen, you are also emitting 11 tons of CO2. So this is the main way of producing hydrogen worldwide today, but intensively emitting some CO2. Then there is another, and this one is called gray hydrogen. Then moving to the central process, it's called blue hydrogen, low carbon hydrogen. It's basically the same process as the previous one, but in this case, you are capturing the CO2 from the process and capturing and storing it underground. So it could be through a salt cavern or depleted oil and gas reservoir, but basically the idea is really to capture the CO2 and to keep it. But still, with this process, you are still emitting 4 tons of CO2 per ton of hydrogen. And then the last process, it's a bit different, still a chemical reaction, but you are using what we call electrolysis, so using electrolyzer. And to do so, you need some power and some water to produce hydrogen and oxygen. And obviously, in this process, the idea is to use green electricity, so electricity coming from solar and wind and wind production, so that at the end you are producing green hydrogen without emitting 1 single ton of CO2 per production of hydrogen. So obviously, ENGIE is fully focused on the green hydrogen part, which is the one with electrolysis. Okay, now moving to what is the current situation in terms of hydrogen today. So today, as you may know, there is already a production of hydrogen. And as you can see, 95% of this production is done through fossil fuel, and mainly 50% of that it's through natural gas, as explained previously. And only 5% is done through electrolysis. So just to make the story simple, we can assume that almost every ton of hydrogen today is done through fossil fuel. Now, in terms of usage, as you can see in the graph on the right, 53% of the overall production is done for ammonia and 32% refinery, the rest being methanol and others. So in a nutshell, if you want to easily decarbonize a part of the industry, a way to do so, it's basically to use electrolysis instead of fossil fuel to produce hydrogen in order to produce ammonia. And this is what we are going to see in the next slide. Just for you to know, ammonia today, the production of hydrogen to produce ammonia represents more or less 1% of the total CO2 emission worldwide. So it's only 1%, but still it's big numbers. So I'm going to skip this slide because basically it will not bring a lot. So now let's jump to the project that we are working on within ENGIE. So it's not the only one project. Obviously, we've got more than 70 projects worldwide to develop some hydrogen. This one is specifically for hydrogen and is located in Australia. It's called the Pilbara Green Hydrogen Hub. So you can see here two pictures of the current plant. So there is a plant, one of the biggest of the world's plant of ammonia production. It is owned by Yara, which is a big chemical production based in Europe. So this plant is in Western Australia, as you can see here in the map. So it's in Dampier, and is producing more or less 1 million tons per year of ammonia. This ammonia is done through hydrogen, which is produced by SMR, so natural gas. And the ammonia is produced and then consumed domestically, so in Australia, but also exported in all South Asia, as you can see in this map. So what is the idea of this of the project that we are working on with Yara? It's basically to take profit of the very cheap renewable in Australia. Why? Because basically Dampier is located more or less in the middle of a desert, so with very strong radiation capacity, so very low solar plant in terms of price, very cheap power prices, let's say. So the idea is really to massively invest in solar assets to produce hydrogen through electrolysis and to replace the hydrogen which serve as a feedstock for the ammonia from natural gas to electrolysis, so from gray to green hydrogen. So in terms of more concretely, maybe in terms of phasing, so we currently are working on a plant of 10 megawatt electrolysis. So we expect to put this plant online in 2023. So as you can see, in order to supply ammonia with hydrogen, it will represent only 1% first of their needs, and the remaining 99% will be still done by the SMR production. And then from 23 to 2030, the idea is to scale up the electrolysis plant up to 1,500 megawatts, which is huge. 1,500 megawatts represent more or less the capacity of a reactor nuclear plant. So it's really huge. And so that we will have the possibility to supply fully almost 1 million tons per year of ammonia in Australia. So the end point would be to avoid up to 1.4 million tons per year of CO2 in 2030. And then, so as soon as we've got a large production plant of green hydrogen, the idea is not just to sell hydrogen for ammonia, but to start building a hub, meaning that this hydrogen could also serve for heavy mobility purposes or for gas blending in the existing gas network in the region. So massive investment, massive project, and very strong impact. As you can see, 1.4 million tons per year of CO2 avoided. Now, so maybe because it's a project in Australia, so making the link maybe with you today, the US also is a very big producer of ammonia, especially in the Gulf Coast in Texas. You've got companies such as OCI, Yara, who are big players in the production of ammonia. And they are all working on moving from gray hydrogen to green hydrogen in order to produce ammonia. And just to give you an example, there is a plant not so far from Iowa University, basically, Iowa fertilizer company. It's like 70 miles from the university, and they are also working on a possible way to move from gray to green ammonia. So just to sum up very quickly, if I still have 1 minute. So today, hydrogen serves as a feedstock to produce ammonia. Today, it's mainly gray hydrogen. There is a simple way, or at least a physical way to move from gray to green, which is electrolysis. That could avoid 1% of the CO2 emission worldwide. And there is plants all over the world of production of ammonia, also in the US. So this is clearly a sector where ENGIE want to invest in order to decarbonize this sector. And maybe we will come back on this during the discussion, but mentioning that obviously all that has a cost, because producing hydrogen through electrolysis is more expensive than the way with SMR, with natural gas. So at the beginning, in order to initiate this business, we will need some subsidies to do so. And basically in Australia, we have received some subsidies to start doing the first phase of the project. I stop here because I think that I already passed the 12 minutes, and happy to answer your question later in the webinar. Thanks for that.
Thank you so much, and thank you for staying on time. So in terms of questions, I assume we'll be passing a mic. I should know that, I'm sorry, as the moderator. But that will happen at the end after the 4 presentations. So next, we turn to Matthew at Block Power.
Great. I'm going to share my screen here. I'm having my computer is not wanting to let me share my screen. Any chance someone on y'all's end can share the presentation that I sent over beforehand? Sorry about that.
Yes, you'll just need to let us know when to advance slides.
Okay, perfect. Well, then I'll jump into it while y'all are pulling up the first slide here. And thanks for bearing with me. So hello, everyone. My name is Matt Goff. I'm here on behalf of Block Power. I'm based in Oakland, California, and work in a project operations role. I've been at Block Power since January of this year, but I've been working on building decarbonization issues since 2019 at the Sierra Club. I want to talk today a little bit about what Block Power does and sort of what our thesis is around building decarbonization and the need for it. So we were founded as a company in 2014 to help play a role in solving the climate crisis. So if you dig into some of the data behind GHG emissions, you'll find that about 10% of our greenhouse gas emissions come straight from the homes and buildings that we live in. And almost a third of our greenhouse gas emissions as a country come from the building sector at large. This essentially means that we cannot solve the climate crisis without solving the building decarbonization issue. And so Block Power was founded with the express goal of electrifying buildings all across our country. The parallel sort of mission of Block Power is to ensure that folks who have historically been left out of the clean energy revolution, historically disenfranchised communities, low-income communities, communities of color, also have a seat at the table in this conversation around decarbonization of buildings and the benefits that this can bring. And so in this overview today, I'll talk a little bit about how we aim to do all this work. Next slide. So in this slide, I just want to ground us in what we mean when we talk about building electrification projects. And then I'll share some examples of how this plays out in the real world. So when we're talking about building electrification, we essentially mean replacing fossil fuel appliances like gas furnaces and oil burners with ultra efficient appliances like heat pumps for space heating and water heating. It means replacing gas stoves with induction stoves. And it means general energy efficiency measures to capture the benefits that these ultra efficient appliances like heat pumps can bring to a home. We also take the opportunity that our retrofits provide to address deferred maintenance in homes. So sometimes there are instances of mold or asbestos or leaky pipes, what have you, that we can work on while we're doing this broader electrification retrofit. So I've got a couple of different building types here that will help to illustrate what this work looks like. In the first example with the single family home, this building owner was interested in electrifying their home, but the barrier for them was the upfront cost. So for folks who are not familiar with the cost of a retrofit, even for a moderate retrofit, you can be looking at easily $20,000 to $30,000. And there are a lot of people out there, myself included, who don't have $30,000 in the bank to do a building electrification retrofit on my property, despite the benefits that that would bring to the lived experience in the home and the sort of increased value that you'd be bringing to your building. So Block Power aims to solve this particular challenge within the building electrification space by offering a no money down 15-year lease that allows customers to break up the large one-time payment of a building electrification retrofit into a low monthly payment over the lifespan of the equipment, 15 years. This cost breakout is also offset by the energy efficiency improvements that we see in building electrification retrofits. So in some of our projects in the Bay Area of California, we're seeing energy improvements upwards of 40%. And so that's driving down people's utility costs and making this proposition more cost effective for more people. In this next example of multifamily buildings, I want to talk a little bit about sort of the home comfort element. So some people want to upgrade their homes because the heating and cooling systems just don't feel good. So you might have a furnace in your home that's blasting hot air in one room and it's 80 degrees in one part of the house. But in the other part of the house, because there's not good ventilation, it's like 55 degrees and you need a jacket. So while the average temperature in your house might be 70 degrees, what you actually experience is one of these two extremes of like sweating in your own home or needing a jacket. Heat pump retrofits can be a great way to improve the like lived experience and comfort of your home. So you're actually having that like 70-degree comfortable temperature throughout your building. And then the final example is a house of worship. So Block Power prioritizes doing work in houses of worship because it's really an opportunity to bring the benefits of electrification to a wider swath of the community faster. So prioritizing spaces like these allows us to help folks get exposure to building electrification. And in this example in New York, we were able to install a heat pump system, which also brings air conditioning. So heat pumps can run backwards, so they can heat your home, but they can also cool it. And it allowed the church to start offering services in the summer again. So the church started having weddings in the summer again. They started having other community events because it was comfortable and folks weren't sweating. And so there are a number of reasons why people will choose to electrify, and we aim to package those benefits to individuals so that they can experience that. Next slide. So how do we actually do this work? So this slide aims to illustrate how we enable projects through public-private partnerships. So Block Power is a venture-backed startup. We will go out and raise project development capital from institutional investors to fund clean tech infrastructure improvements. Essentially, that means we go out and raise the money that allows us to offer these 15-year leases to customers so they can avoid those upfront payments. We tap into networks of private partners to drive down project costs and get support on project management. We have partnerships and relationships with Microsoft, the Bezos Earth Foundation, other entities like that allow us to do more projects in more places. When we're doing our building electrification work, we really have an eye towards delivering additional value. So one view of electrification is already what I've outlined, installing heat pumps, doing energy efficiency measures, but there's also a real opportunity to modernize our buildings by incorporating low-cost Wi-Fi into these structures. It's a way to bridge the digital divide. It's a way to bring more people into the 21st century. And it's a real added value that gets more support from the community when we're looking at enterprise scale investments. We also deliver additional value on the health front, which I'll talk about in the next slide. But there are a number of intersectional benefits that can be addressed in building electrification. We also look to support from local governments. So cities provide Block Power with support in the form of outreach, data, staff activities. We've also seen support in the form of funding for pilot projects. So, building electrification is a pretty nuanced issue, and the challenges of one community don't necessarily match the challenges of another community. And so pilot projects give cities really useful insights and data for how they might electrify the particular building stock that exists within a given community. And so we package all of this work, this public-private relationship, and we turn it into building electrification retrofits for the community. We also really lean into the job creation element of it, which I will talk about on the next slide. So let's go to the next slide here. So there are a number of benefits that electrification provides. So one of the big ones is on health. So I mentioned that we do, deferred maintenance and remediation in homes. We find in a lot of properties that we work on that folks have mold or asbestos in their property. There's a need for lead remediation. And so our retrofit works allows us to address this deferred maintenance that maybe somebody has known about for a while, but hasn't been able to because of cost. There's also a really important health benefit in the form of replacing your gas stove with an induction stove or election stove. So studies have shown that kids who grow up in homes with gas stoves are 42% more likely to develop asthma in comparison to kids who grow up in homes without gas stoves. It's kind of like a shocking statistic and something that many of us grew up with and maybe didn't realize we were being exposed to these pollutants. Another study by the Lawrence Berkeley National Laboratory found that in a majority of homes with gas stoves, when those stoves were on, the indoor air quality levels were so bad that they would be illegal if they were found outdoors. And so there's a growing body of research out there that shows that gas stoves specifically and gas appliances at large are not just bad for the climate, but they are bad for public health. And so a number of communities and individuals decide to make these retrofit upgrades for the benefits in the health category. Their energy and cost savings. So I think I touched on this earlier, but in a number of our projects, we see energy efficiency savings of upwards of 40%. And so this makes the proposition of electrification cost competitive today. And as we move towards more renewables being introduced to the grid, greater investment in renewable energy from local, state, and federal governments, I think that these cost savings are going to grow in the coming years. And so there's not just benefits today, it's going to be—
You have 1.5 minutes.
Great, thank you. And then the last piece on this slide is local economic development. So right now, there's a real gap in the number of contractors and developers who can do building electrification retrofits. And so Block Power is invested in training up the next generation of this workforce who can do these retrofits and get paid a family-sustaining job that provides a high road wage. So we really look at this as an intersectional package. We'll do next and last slide here. And so this slide just illustrates how we think about flipping the typical adoption curve paradigm on its head. So on the left-hand side, you can see the typical adoption curve of early adopters, majority adoption, and then laggard adoption. This typical curve brings the benefits of new technology to folks who are in a position to make more risky investments that have a higher potential for payoff, but it oftentimes leaves behind folks who don't have the economic flexibility to make early adopter investments. Block Power aims to create programs that serve low and moderate income communities so that those folks can also participate at the early adopter phase, reap the economic and health benefits that are associated with clean technology. So we don't want to recreate some of the lopsidedness that exists in solar and EV adoption. We want to make sure that LMI communities, again, have a seat at the table as we electrify our buildings and move into the future. So last slide, that is what I've got. Thanks for your time today.
Thank you very much. I hope people are writing down questions. Question cards were passed out. If you're online, put your questions in the webinar Q&A. Mark?
Thank you, Charlie. And while the slides are being set up, I would like to thank Professor Stanier and the organizing committee for the opportunity to speak today. My talk is going to focus on renewable natural gas. Thank you. And so more specifically, renewable natural gas in the context of the state of Iowa, we'll talk about some opportunities to decarbonize the production of natural gas and how we might accomplish that. Next slide, please. And so before I do that, I would like to put into context the role that natural gas has played in multiple sectors in the United States. And so as Professor Stanier mentioned earlier, thank you. Natural gas consumption overall has been increasing significantly. So roughly about 2 to 3% per year since 2010. And among other types of fuels, natural gas has been probably the fastest growing fuel in the US. We use natural gas for a variety of purposes. Almost every industry, with the exception of the transportation industry, relies significantly on the use of natural gas. I think this is something that most of this audience is fairly familiar with, but sometimes we can be surprised by the percentages. So in the power sector, about 40%, and then in the industrial sector, about 33%. Oh, I think, thank you. Thank you. And so with this increase in the use of natural gas, we've actually seen that natural gas has played a significant role in reducing the emissions of our energy sector. You could say that natural gas has been one of the primary reasons why the emissions have decreased almost 20% since the year 2000. Of course, renewables have played a significant role as well, but we can't underscore how much natural gas has been a significant part of this development. But nowadays, we're trying to accelerate that transition. We're trying to reduce our emissions even further. And when you look at natural gas technologies, I've broadly grouped them into these 4 categories. At the very top, you have your conventional fossil-based natural gas negative emission technology solutions. These would be using carbon capture and utilization, for example. It doesn't quite get you to negative, but it gets you fairly close to carbon neutral. You could also sequester the carbon. And both of those solutions are among the more expensive side of strategies that we could use. On the more environmental side of strategies, but slightly more expensive, you have renewable natural gas and carbon capture, which would effectively be a carbon negative solution or strategy to decarbonizing the natural gas sector. Now, the challenge with renewable natural gas, as many of you may know, is that for many centuries, it has not been able to compete economically with conventional natural gas. That's starting to change for reasons that I'll get into in a minute. But for those of you who may not be as familiar with the technology, we're talking about digesters that can be relatively simple to very complex reactor designs that take multiple types of waste, ag waste, food waste, all types of biosolids, and convert it into a biogas that once purified can substitute natural gas in almost all applications. In addition to that, we get a solid and liquid digested product. That product has a lot of value for our farmland, but additionally, it can contain some carbon depending on how you operate your digester. That would also provide some carbon credits, but most of the carbon credits would come from maybe capturing the CO2, which is part of the biogas and of low economic value. Now, what is the potential? And I think this is where I hope to provide you some incentive into looking into these technologies. Thanks to support from the Iowa Economic Development Authority, we've been working on mapping out sources for renewable natural gas across the state. If you look at total natural gas consumption, Iowa consumed about 404 billion cubic feet of natural gas in 2020. When you look at the biogas potential, we estimate that we could produce about 120 billion cubic feet of biogas from all these sources. Granted, not all of these are easily accessible, so this is a theoretical maximum, and the actual potential might be much lower, but this just gives us a target that we can work towards. The primary resource that we have in Iowa are animal feedlots, so swine manure, beef manure are sources that we could use to produce biogas today. We also have landfill transfer stations and other types of industrial and commercial facilities. In terms of its ranking with this US, Iowa is number 8 in the potential for biogas production. But what does that translate into in terms of carbon savings? Now, life cycle analysis used to be a relatively complex and often misunderstood technique until a lot of the incentive programs have made it necessary for companies and academics like myself to really dig into and understand how the emission landscape translates. In the case of natural gas, we already know that natural gas has a lower footprint than gasoline or diesel, but it's still relatively high, about 88 grams of CO2 per megajoule consumed. As we move towards the right in the figure here, you can see that renewable natural gas can have a footprint of between 49 on the high side to negative 310 grams of CO2 per megajoule. That negative value is driven by the avoidance of methane emissions that would occur if you leave manure and other types of organic waste in the field or on a landfill. That number is what drives a lot of the incentive programs that I'll talk about in a minute, and part of the reason why we see a great demand for renewable natural gas facilities. Here in Iowa, we don't have as many locations where we could take advantage of that low value, but we do have significant ways of taking advantage of renewable natural gas from high biosolid digesters, and with gasification, we could also achieve values of about negative 100 grams of CO2 per megajoule. So what does that translate into? So we did some rough calculations based on the types of biomass that we have available. And on the left side, you have an estimate for the emissions that Iowa would generate just using conventional natural gas. And on the right side, you have what the emissions would be if you replace some of that natural gas with these renewable biogas resources. And what you can see here is that we can significantly reduce the environmental footprint of our sector if we were to harness these renewable natural gas resources, essentially down to 20% or less. And so this just underscores what I tried to show in the previous slide. Out of the 16.6 million metric tons of CO2 that we emitted as a state, we could reduce that significantly by more than half, just using biogas. Now, as I mentioned, it's expensive to operate digesters. And so Professor Steinier asked that I speak a little bit to the economics. I'm going to just speak very highly, at a high level, regarding the economics of deploying these facilities. What's driving renewable natural gas today is that if you produce RNG from dairy waste, you can get upwards of $40 per million BTU that you produce. So I don't know what the price of natural gas is today, but historically, right, $3 to $5, you could get up to $40 per million BTU. Now those values again are from dairy digesters, which you don't have many in the state, but you can still get fairly significant values from other types of renewable natural gas. Our group conducted a study with the city of the city of Cedar Rapids to look at some of the resources that are available within the region or the urban community. And so the map that you see on the right is a hypothetical map, right? What could happen 20, 30 years from now if we could convince most farmers and industrial facilities with high organic waste streams to install digesters. We spoke with the wastewater treatment facility here as well. And what they told us is essentially what has been mentioned before. Getting these digesters connected into the infrastructure, building pipelines, access, all those pose very significant challenges that hopefully our legislatures and companies can figure out ways to facilitate that process. I believe that right now, given the incentives that are in place, we have a significant opportunity and a short window to build these digesters. And once they're built, they'll keep running. And so with that, I'll conclude my talk.
Thank you. Let me say again, happy Earth Day. Good to see you all. I'm going to talk about the university's work. So we've kind of gone from global with hydrogen to now the more local and just right here in this space. And so while my slides are coming up, I really, my first few slides are going to be about how awesome it is to be working in a place where we have such a purpose behind what we do. So my job is to provide the utilities to this campus and all the things that happen on this campus. And so that includes a world-class hospital, research, students who are making a transition in their lives and doing the learning that goes on here. So my job is mostly to stay behind the scenes. And I should say my team's job is to stay behind the scenes and make sure that all of those things happen and really facilitate that. So that, you know, the lights are on in here and we can have this great conference today. That's my job. In the end, having that kind of a purpose, it makes this a really great place to work. And in addition to that, we have some really exciting things we're doing with energy. It's a great time to be in energy. And that's really what I'm going to get into. I will also say, though, we do a lot of work behind the scenes in the utility department and facilities management. But in addition, we do get out and we make this campus a lab for sustainability and for energy. So if you're an existing student and you want to get involved, reach out to the Office of Sustainability or your professors. We are always doing work with students to make this a place where you can not just learn the theory, but you can get your hands dirty in doing energy work, like here, literally getting hands dirty, making a rain garden with the Office of Sustainability and our landscaping crew. So with that and what we do on this campus, I want to give you some scope of how big of an opportunity we have and why it's so exciting to be part of the energy transition for this university. And I know this is the same in many other universities, right? But the University of Iowa has a very big impact. And so decisions we can make here and planning we do here can have a major impact. And the reason for that is the size, 42,000, the equivalent of 42,000 Midwest homes is the annual energy use of the University of Iowa. That's just a huge number. And so things we can do here can lead the way, can be an example, and can have a really big impact. So to put that into context, 42,000 homes equivalent energy, that's the same as Iowa City and Coralville households, according to the census data. So what we're doing really translates and could be the same as taking this whole campus in a decarbonization path, or this whole city in a decarbonization path. This has been talked about a number of times here in this morning's session and also last night by Saul Griffith. You know, there's been a lot of focus in the past on renewable electricity, right? And so now we're getting to the point where the conversation has shifted and needs to shift. And the University of Iowa is taking a hard look at what we do next. My numbers are a little different than some that others have shared because I tend to focus more on the Midwest, right? So nationwide numbers are different than this, and that's what some others have shared. My Midwestern numbers say that in your average home, and this is probably most of us, 35% of your energy use comes from electricity, while the other 65% is being burned in your furnace. The correlation to that is that the University of Iowa campus is very similar. So we use 25% electricity and 75% steam. And so as you look at those two pictures, the top picture on the right is a home furnace. And the bottom picture is the steam plant at the University of Iowa, which is essentially the university's furnace. And we're trying to decarbonize both of them, I think, in very similar ways. And we face the same challenges, which is what we want to talk about today, is what those challenges might be in decarbonizing. So really, as I see it, we have two options to decarbonize, both at the University of Iowa and potentially in your home. Mark, I did not put biogas up here. I probably should have, but the first thing that came to my mind was hydrogen, because you can start burning renewable stuff instead of natural gas, right? My view is that's a little further down the road. And I think there have been some comments to that effect, but it's not that fuel needs to be developed, but it's not such an immediate option for all of us. And then the other option is to stop burning stuff altogether and use electricity. And I think that is the way the university is headed in the short term, maybe even the long term. But that is also sort of the idea, I think, that has come out of this conference as much as anything, is that the more you can stop burning natural gas and start using electricity, that's the next path, that's the next step. And I think that maybe hasn't been talked about enough, but we're going to start that conversation. And I think that's the way the University of Iowa is going to head. So let me get into some of our history here. We have been burning renewable stuff at this campus for quite some time. Back in 2003, we started burning hulls from an oat processing facility in Cedar Rapids. And so we've been on this path for quite some time of decarbonizing. It's just recently shifted more to the electrification side. We also have miscanthus grass on the right that we're growing. We have 1,100 acres that we're growing. And that miscanthus grass goes into energy pellets, which are the picture in the center. This is a fuel that we're using, and we still are in the process, but nearing the end of getting this campus off of coal. I will say that those energy pellets, they are a fuel that we have chosen and I know is not a perfect option. So we'll just say that right up front. There are some hydrocarbon-based materials in those pellets, but those are things that make them a viable fuel and an economical fuel for this campus. And so that's how we're going to get off of coal, hopefully in the short term. From a planning perspective, we're looking now at decisions that will lead to the decarbonization of this campus in 5 or 10 years. So our focus has already shifted from a planning perspective. We're looking at how we electrify and get ourselves off of natural gas. And the great thing about some of our past decisions and using these fuels you see on the screen, that has kept us from going to 100% natural gas, which would make that job of getting off of natural gas significantly more difficult. We have many more options now because we have taken the path that we have. And so the University of Iowa is in a good spot. And I think we can be a leader and show people what is possible. In the end, I do think hydrogen it will become a fuel of the future. I don't know that it will ever be something that colleges and universities will be able to take advantage of. I think we need to look more at electrification. We have better options in that place. I don't want to put the university in a position where we are in line to have to pay for hydrogen along with thousands of others who also want to decarbonize in that way. So I think we have some better options. We also have the option of continuing our work with biomass and using biomass in natural gas boilers. I think that is maybe a little further off also, so just my opinion on that. kind of getting to the end of my slides here, the options I think for colleges and universities is to use either electric boilers, which is the top right-hand side, which I think is the way the University of Iowa will be going short term. And then a longer term, there are already some campuses that are switching to looking at geothermal. Now imagine geothermal in your home is significantly more expensive than just replacing your furnace, right? That's one of the issues that got brought up just in the last presentation of why people aren't widely adopting things like geothermal and heat pumps. Well, you can imagine the cost difference when you multiply that by 42,000 for the University of Iowa, right? So we've got to figure out how we may be able to switch to a geothermal system economically. That's the biggest hurdle for colleges and universities going geothermal, is the economics of it. But there are some that have done it. So you look at Ball State, they went 100% geothermal. Princeton University is on a path to phase in geothermal, as I understand, between now and 2040. One of the things I will say too that makes it maybe a little easier for those colleges and universities to go 100% geothermal that the University of Iowa has a little more difficulty, is you may not realize it, but those colleges and universities are between around a third the energy footprint of the University of Iowa. We have a lot of things going here that take a lot of energy. And so one solution probably won't work for the University of Iowa. It's going to be a combination of biomass, geothermal, electric boilers, all of those together we're going to need because of our size compared to other colleges and universities. So I do think that we will be looking at electric boilers. So right now, to wrap it up, we are currently on the left-hand side where we are using biomass and other fuels to displace carbon. I think our next step, and the things we're planning for today that will get put into effect over the next few years, will be possibly installing electric boilers to start to reduce our natural gas use. And then 10, 15, 20 years from now, if we are still burning some amount of natural gas, I can see that then may be displaced by hydrogen or biogas to get us the rest of the way to decarbonization. But I do think the electrification in the center is really the key to where the University of Iowa needs to go next. And so that's our path. And I hope talking about that electrification here at the university will also translate then to a conversation where people think about the same thing in their homes, because it really has to happen in both places for us to meet our carbon goals. And hopefully the University of Iowa can be a leader and show that it can be done, especially on a large scale. So thank you.
All right, just thinking about time here. So it's 9:53 and the session goes till 10:15. So we have about 25 minutes for questions. I can't see the online questions, and that was my error. If any. Great. Okay, so I'm going to kick off with the question I gave people before the session, and that's, and we're going to go round robin across all four. If you don't want to answer, you can pass. But what's one thing that students can focus on here at the University of Iowa if they found these four talks like light their fire? So we'll go in order of how you presented. So Benoit.
Yeah, so I don't know if I'm really answering the question, but I would say that an advice that I could tell to your students is just to find a company when they will leave the university, which are deeply involved in decarbonization business. So could be utilities, could be tech company involved in new solutions, could be in university as well, in order to form some new students, but really to be involved and to be engaged in this very strong move which is absolutely necessary for the future. So maybe it's a very high level answer, but this is really the first thought that I have to answer this question.
Thank you.
I think that there are a number of ways students and people who are interested can engage in the topic of building electrification. I think that building electrification as like a technology, as a policy solution is still like fairly nascent. And so there's just a lot of opportunity for students and interested people to go out there and do more research to understand what these solutions could look like in your individual communities. And so understanding the language of decarbonization is probably a good place to start. And then from there, engaging with local governments, decision makers to understand what sort of policy solutions are possible in your community is a great pathway to go down. I also agree with the sentiment of working with a company or some entity that is working to implement building decarbonization practices. So maybe while you're in school, build up this knowledge base, and then once you graduate, look for a company that can help you achieve the interests that you have.
Thank you. Mark?
Thank you, Charlie. Well, I will plug a few activities that we have at our university. So at Iowa State, we have obviously student organizations like Engineers for Sustainability that you can get involved in. Even if you're not a student from Iowa State, we welcome University of Iowa students. And those organizations do activities both within the community and even internationally that help promote energy and sustainability. We have courses, we have a course on engineering, economics, and policy that look at some of the issues around adoption and innovation of energy technologies. So that's something that you might want to look at as a course. And as was mentioned earlier, we usually have companies that come to campus to hear about some of the innovations and projects that even our student entrepreneurs are working on. So there are many opportunities on campus.
I'll add to something that I said in my presentation, and that is I think students can get involved, and I know a lot do, but I think students can get involved hands-on while they're here. And so they come out with not just the theory, but also hands-on and see what it really takes to implement projects. So I think that's a start. I also am a big fan of the idea of change management and how that can be something that if you know something about that, when you get into the world and become a leader in your organization, wherever you choose to go work, I think that's what we need. There's a lot of change that's involved with all of these implementations, and I think that's a big part of it. So I'm a big fan of an author named John Cotter, and so if anybody would read an article about his work on leading change, to me, that's something that you've got to take into whatever job you go into, so that you kind of know the steps to go through to implement a big change, which is what we're talking about. These are big changes and need a lot of people who have bought in and understand and know how to make it happen. And so the more students we have leaving colleges and universities that know how to join organizations and help them change, I think the better off we will all be.
Thank you. So an audience question. This one's pretty directed. I think you'll see who has to answer this. How do we get a tour of the University of Iowa power plant and all of the energy infrastructure on campus?
I will venture that's mine. You can go to the University of Iowa Utilities webpage, and there's an email from me there. So feel free to reach out directly to me, ben-fish@uiowa.edu, and we can certainly set up tours. We give tours very frequently, and it's just one of the things I think that we offer that for students to be able to see sort of what we've done, how things work. You might be surprised at how big the infrastructure is that's required to heat this campus and cool this campus. So we're very happy to give people tours, because I do think that's a big part of learning about what we do and even helping have a voice in what the university's next steps are.
Thanks. This one's for Benoit. What are the factors that control the price and efficiency and suitability of sites for green hydrogen production?
So you have to know that more or less between 50 to 70% of the cost of hydrogen produced by electrolysis is linked to the power supply. So I would say that the main driver for the economics for electrolysis is first to get access to cheap renewable resources, power renewable. So that's really the first point. Then in terms of efficiency, today efficiency of electrolysis is more or less 80%. There is a lot of development ongoing and research ongoing on the electrolyzer all over the world. We believe that we could reach 90% pretty quickly. Obviously, which could help, it's a massification of the market. So we see a lot of new projects on hydrogen. So we believe that the capex, the investment cost to produce electrolyzer will decrease pretty sharply in the same dynamic that we have seen for the solar panel, for instance. So first driver, power. We also believe that decrease of electrolyzer could help. Compared to the way to produce hydrogen today, electrolysis is still more or less 2 times more expensive than producing hydrogen with natural gas. So we will have to review a bit this number because given the recent increase of gas prices, it could increase the competitiveness of electrolysis, but I think that we are still in between 2 times more expensive with electrolysis. And just for you to know, there is a production tax credit discussion ongoing today in the US. It was embedded in the Build Back Better Act. So most likely this PTC will not be within this Build Back Better Act, but will be separated and most likely voted in the core of this year. So this production tax credit could decrease the hydrogen price produced via electrolysis by $3 per kilogram, which is huge compared to an overall cost today of $4.5 more or less per kilogram. So way to decrease electrolysis cost, cheap renewable, massification of the electrolyzer capacity, and production tax credit in the US.
Thank you. Next question, I'm gonna put to Mark and Matt, and as citizens, if you wanted to move either the type of low income and middle income housing retrofits that Matt was talking about, or if you wanted to move biogas generation forward, what are some things that people who are not researchers, not in positions of power, but just citizens, how can you get involved?
Yeah, I mean, this is a good question. I can take a stab at this. I think that, one of the biggest barriers to the electrification of low and moderate income households is cost, right? We talked about average project cost on a single family home, being upwards of $20,000 or $30,000. That's a lot of money no matter who you are. And so when we're thinking about what's needed to change, we need to drive down these project costs. And I think that there are a number of ways that we can do that. So the cost of the equipment is one way to drive down project cost. If the heat pumps themselves, the induction stoves themselves cost less money, we can make the overall project costs lower. And so how does that connect with what an individual can do? I think that there is a real opportunity for individuals to engage in local governments with regulatory agencies to advocate for their support for building electrification policies. Greater policy adoption means greater economies of scale, more heat pumps being bought by more consumers across the globe, and that drives down project costs. And so I think that people we have the technological solutions today. We just need greater adoption and buy-in from our sort of regulatory and government bodies. And so I think people voicing their support for electrification because of the benefits that it brings from a climate perspective, from a health perspective, and increasingly from a cost perspective, is something that will directly benefit low and moderate income communities who are looking to electrify in the moderate term.
Thanks. Mark, do you want to talk about citizen advocacy for biogas?
Happy to. So I think one of the things that we as citizens don't always recognize is that our communities, our municipalities have systems in place to treat our water, to manage our waste, that sometimes already use biogas or could use biogas if the community demands it or suggests it as an option. And so both in the city of Ames, the city of Cedar Rapids, and in Des Moines, I've had the opportunity to meet with their waste management facilities. And they've all said, we like anaerobic digestion, that all three have anaerobic digesters in place, but the funding that they get is relatively fixed, and they don't always have solutions to, for example, implement renewable natural gas because that wasn't part of the original mandate. So as we become more informed about these solutions, speaking to our local councilmen and municipalities can help promote these solutions.
Thanks. There's a question for Ben. Why hasn't the UI installed large-scale solar arrays?
Thank you for that question. It's a really good one, and one that I think I glossed over in my presentation. I think I know, and I think a number of folks do, but the Iowa grid is very renewable already, right? And so I think as we look at what we are going to invest in on this campus, our investment needs to look at decarbonizing through our switch, and again, our switch away from natural gas, because on this main campus, we already receive 80% or 87% renewable electricity from our electricity provider, and that number will only increase. They have a goal to be 100% renewable. For us, the investment in additional renewable electric generation doesn't make as much sense as trying to use the renewable electricity that we can buy from the grid and turning that into the steam or the heat that is 75% of our energy use. So it's a very good question. But I think it's a matter of where we put our resources, and to us to put more renewable electricity into a system that is already very highly renewable and on a path upwards is just not the place where we want to put our funding. We really want to put our funding into getting off of natural gas, which requires a boiler, something that replaces steam rather than electricity. Thank you for the question.
Mm-hmm. Mark, could you talk a little bit about your life cycle assessment boundary as you continue to expand the boundary to include more of the CAFO operations and the production of feed for the animals and then fertilizer to make the feed, it becomes less favorable. So where do you draw your lines?
That's a great question, and I wish I had some slides and formulas to really dive deep into that. I appreciate the question. So certainly the life cycle assessment boundary for anaerobic digesters is one that has been a subject of a lot of debate recently. And the main reason is because California and Argonne National Lab in their GREET model decided to draw the boundary around the notion that waste biomass like manure from dairy cattle, if it's not using a digester, would emit methane. Certainly, if you include the dairy operation within the boundaries of the system, you may not get carbon negative numbers or definitely not as favorable as they are. But part of that reason is because we're trying to move away from what's called business as usual scenarios. The idea is that a business as usual scenario today is that fertilizers are done primarily from fossil fuels. Manure is usually left on the ground for a good reason. It provides nitrogen, but it emits a lot of methane. And so if we are going to reduce our net emissions, we need to convert from those business as usual scenarios to more sustainable scenarios. And today, certain organizations have chosen to draw the boundaries around those particular activities. It does favor renewable natural gas. And I believe if you're for reducing emissions, that's a favorable system boundary. In the future, it might change, but I believe that that's probably the correct solution today. Thank you.
Thanks. And this is for Ben and maybe for Matt. Decarbonizing a large comprehensive set of buildings, a campus, right? So for Ben, the question is, could you talk about decarbonizing the hospital? And I guess for Matt, it would be, has Block Power done anything at that sort of multi-building scale? I'll let Ben start.
Right, thank you. Yes, a lot of hospitals, including ours, have a central utility system. So in some senses, it may be easier to decarbonize because you've got really big equipment, which is very efficient. And that's why it was installed in the first place, to heat and cool an entire hospital complex. The thing about making the switchover, which I think is sort of the basis of this question, is that when you make a change, you've got to make sure that you do it in a measured way so that you don't lose the reliability and impact the day-to-day operation of that hospital. That's the biggest barrier we have most of the time to moving more quickly than we currently do, is because we have to make sure that we keep things running on this campus. That doesn't mean that it can't be done. There actually are benefits to having these systems that are centralized, because then you can do one big project at scale and look at a really big geothermal field, for example, rather than having the cost of going building by building. So I think we have some benefits because we are so large, and that when we do a project like maybe a geothermal type of system, we will be able to do it at a big scale and get good pricing for it. I think on the other side, the difficulty is that while we're installing that geothermal field, we have to make sure that as we start it up and switch over to that system, we have to make sure that that hospital keeps running and doesn't even realize that we're making a change. And so those are sort of the factors that I see that I think are the basis of that question.
Thank you. Matt, do you want to jump in?
Sure, yeah. So Block Power has worked on large multifamily buildings on the East Coast in New York City, as an example. I think that the key pieces of those projects' success has been from getting stakeholder engagement across the community. And so Block Power's model includes setting up community advisory boards to get input on the specific improvements for sort of a large multifamily property that has a lot of different perspectives within the building. And then it also looks at bringing in perspective and buy-in from outside the building. So we, in some of these projects, have gotten subsidies and incentives from local governments to help lower the project costs. We look at some of these larger projects as pilots and examples of how retrofits like this can be successful, so that we're not to the point of disturbing the building's operation on a day-to-day basis. You know, one, for the sake of our company to be more efficient and more effective in future projects, but also as a model for policymakers who are looking at designing solutions, incentives, you know, various carrots and sticks at scale. So on our website, there are examples of some of the sort of specific larger multifamily projects if folks want to get more detail on that.
Thanks. I'm going to wrap it up there. If you didn't get your question answered, Mark and Ben are here, and I know Benoit and Matt will engage with you by email. And just let's thank all our speakers for a wonderful session.